In this video, we want to look at the topic transformers in physics. So we'll be looking at what transformers are, then we'll look at the parts of a transformer, how to draw a transformer. Then we'll proceed to look at the various types of transformers that we have. So we'll look at the step-up transformer, the step-down transformer. Then we'll look at the relationship between some particular parameters that we'll be mentioning when we are drawing the transformers, the relationship between them, how the transformers step up or step down, and EMF. We'll be looking at that, and then we'll be solving some practical questions on this. After that, we'll conclude the tutorial by solving some WIAC past questions on this particular topic, transformers. So this is bound to be a very detailed lectures or teaching on transformers. So get your notebook, get your pen ready, get your calculators ready, because we are about to dive in. All right, so the first thing we'll do is look at the theory part, look at what transformers are, and then the relationship between the transformers. After that, we can look at the calculation part in the next chapter. So what is a transformer? A transformer is a device used to step up or down an alternating current. So let's write that. We are saying a transformer is a device used to step up or down an alternating EMF. Okay, an alternating electromotive force, or basically an alternating voltage, right? So this is what a transformer is. It is used to either step up or step down an alternating EMF, right? That's basically what a transformer is. So let's have a general overview of what a transformer looks like. So basically, a transformer has what we call a soft iron core. So I'll draw the iron core like this. Okay, it has something like this. Then it has, let me use a different color here. So it has some things here, some coils around it. Okay, so this coil has a name. We'll be looking at that. Then over here too, we have another set of coil over here. Okay, and then we have over here our alternating, the source of our alternating current. Okay, connected over here, and then yeah, we have label this part. So basically, it's just the iron core, the coils, these two coils, and then a source of alternating current attached over here. So let me quickly label the parts. So this guy is what we are calling the soft iron core. Soft iron core. Okay, that's the soft iron core. Then this is the AC input, alternating current input. This is our source of alternating EMF. Okay, now the first coil near the AC input is what we call the primary coil. So this guy is what the blue one, the blue coils over there, is what we are calling the primary coil. Okay, now it has, you can see that the coil is wrapped around the soft iron core for a number of times, right? That is what we call the number of coils, okay, or the number of turns. So we use N subscript P to represent that. Okay, so the number of primary coils. Okay, so NP, so we say this is NP turns. Okay, over here we have this. Since this is the primary coil, this is obviously the secondary coil. And then the number of turns is what? NS. Okay, number of secondary coils, okay, turns. Okay, that is that. So we have the soft ion core, the AC input, this over here, and then this is where we have the okay AC output. AC output. Are we okay? But then the distance between this over here to over here is what we are calling the secondary EMF, okay, or the secondary um, potential difference. And then the distance from over here to here, okay, over here is what we are calling EP, which is the primary EMF, right? The source of primary EMF in the core, right? You can see that it is in line with this over here, okay, this side over here, okay. Basically this white one is just for labeling purposes. Okay, so this is basically a general overview of what an alternating current a transformer is, right? So it has a primary core, a secondary core wrapped around a soft ion core, then it has an AC input and then the AC output. Now where the primary coil is, the EMF over there is what we call the EMF of the primary coil, which is represented by EP. Then the output, where the output is, we say that is a EMF of the secondary coil, so we represent that by ES. Obviously the coil on the secondary side is what we call the secondary coil. The number of turns it has is represented by NS turns, and then the primary coil, where the AC input is the primary coil, and then the number of turns is the NP. Then so basically let's have a look at some things we can note over here. So we are saying that it consists of a soft ion core with two coils wound on it, right? So it consists of a soft ion core, with two coils wound on it. Okay, another thing we should know is that the first coil is what we call the primary coil. So the first coil is the primary coil. Then obviously the second coil is the secondary coil. Very good. Now the primary coil is connected to an EMF source. Okay, the primary coil is connected to an EMF source. Okay, so which is the AC input that we have over here. So this is basically the description of what a transformer is. Now let's make some deductions from this, right? So let me make here deductions. Okay, let's do some deductions and see how best we can move from there. So the AC flowing through the primary coil is changing at all times, hence it produces influx in the secondary coil. So the alternating current, okay, flowing through the primary coil over here produces what we call influx in the secondary coil. That is what we need to know. That is the one of the deductions. We'll be using these deductions to derive the formula. That is why I'm taking my time to go through. So we are saying that the AC source or the AC flowing through the, I'll use this as primary. So through the primary coil is changing at all times, hence produces change in flux in the secondary coil. Okay, so it produces change in flux in the secondary coil we have over here. Now another thing is that flux that is produced in the secondary coil, right? The flux produced in the primary coil is proportional to the number of turns and then the current moving through the coil. So if we look at the primary coil over here, the flux produced by the AC input, which is inducing another flux to be produced in the secondary coil. The flux produced in the primary coil is proportional to the number of turns that we have over here, right? The NP. The number of turns on the primary coil, okay, determines the influx of the number of flux or the amount of flux that will be produced, right? So the flux produced by the primary coil is proportional to the number of turns NP and the current IP, okay? And then automatically, if we come to the secondary coil as well, the induced EMF in the secondary coil is also proportional to the number of turns NS and the current IS, which is flowing through it. So we are saying, basically, let's quickly make that. So we are saying the flux produced in the primary coil, okay, is proportional to the number of turns to the number of turns. Okay, the number of turns for primary is NP, okay, and the current IP, okay, which means the current in the primary coil. Now the other way around is true for the secondary coil, so I will not write that, you just quickly say it. So you can write this down. For the next deduction, it's the induced EMF in the secondary coil is proportional to the number of turns NS and the current IS flowing through the secondary coil. Okay, so we are saying that depending on the number of coils that we have on the core, okay, on the soft iron core at the primary side, it determines the number of current that or the amount of current that will flow through that primary coil. The same with the number of turns on the secondary side of the transformer also determines the amount of current that will flow through. Okay, there's a relationship between that. So let's look at that relationship now. We don't know whether they are directly proportional or indirectly proportional, but let's look at, so then the relationship is the current flowing through the primary coil, okay, over the current flowing through the secondary coil is equal to the number of turns in the secondary coil over the number of turns in the primary coil. Okay, now if you look at this is inversely proportional, which means that for the number of current flowing through the primary coil, it is inversely proportional to the number of turns of the coil, right? And then the same thing, the number of the amount of current flowing through the secondary coil is also inversely proportional to the number of turns on the secondary coil. Okay, so this is the relationship. So if you divide this by this, you are going to get this expression. So this is a very, very important expression that we'll be using in our calculation. So we need to hold this expression very, very deep. All right, so let's look at another expression which we'll also be using. So another expression we'll be using, okay, so before we look at that expression, let's look at something. Okay, now if no energy loss occurs in the transformer, then the power output is equal to power input, right? So let's take again. Okay, so we are assuming in an ideal situation where the transformer is so good, so perfect that no energy is lost during the step up or the step down process. Okay, then power output is equal to what? Power input. So let's look at that. So if no energy loss occurs in the transformer, okay, then the power output is equal to what? Power input. Okay, so basically what is power? Power is equal to voltage multiplied by what? Current. This is power, right? Now if this is power, in this case we are saying voltage can also be EMF. Okay, so power in our case over here will either be what? Let's say if you are saying the primary power, okay, the power in the primary coil, it will be what? EP IP. Okay, then the power in the so let me say primary power. So the secondary power, okay, which is the output, the power output. So the primary power is the power input, so this is the power input, and then this is the power output. Okay, so that will also be equal to what? ES IS. Are you okay? So we are saying that if no energy loss occur, then ES, okay, IS, which is the power output, should be equal to EP IP. Okay, power input, or you can rewrite them as this. Okay, it's equal to IP on IS. Are you okay? So we are saying that it's either this or this, right? So this is just like you dividing, making the E stand at one place, and then the current also at one place, the EMFs at one place, and then the current also at one place. So this is the expression that you get. Now remember, earlier on we also said that IP over IS is equal to NS over what? NP. Okay, that is what we looked at over here. So this expression, okay, is what I am quoting over here. Okay, now so if ES, okay, the EMF in the secondary coil over the EMF in the primary coil is equal to the current in the primary coil over the current in the secondary coil, and then again this current in the primary coil over the current in the secondary coil is equal to the number of turns in the secondary coil over the number of turns in the primary coil, then we can see confidently from here that our ES over EP, okay, which is equal to IP over IS, is also equal to NS over NP. Okay, now this is a very useful expression that you are going to be needing for all your calculation. It's two things, right? You either take this expression, okay, and know them off head, or you just know this one off head, and then you are good to go to solve any problem on transformers. Now note that for the EMF and then the current, the relationship is inversely proportional. Are you okay? And then for the current and then the N, the number of turns, it is also inversely proportional. Are you okay? But if you want to take just the EMF and then the number of turns, they are directly proportional. So you can see ES at the top here, NS at the top here, EP at the top here, NP at the top here. So if I want to write this in another way, I can write ES over EP is equal to NS over what? NP. Okay, because they have this in common, so it means this is also equal to this. Okay, so basically this is equation 1, this is equation 2. From equation 1 and equation 2 you can get this as equation 3. Okay, don't confuse the positions. Are you okay? So the first thing you need to know is that the current and then the number of turns are inversely proportional, and then this guy is also like this. And once you know that, you don't have any problem, right? So like I said, the ES is the EMF in the secondary core. So this is ES is the EMF in secondary core. EP obviously is the EMF in the primary core. IP is the current in the primary core. IS obviously is the current in the secondary core. NP, okay, is the number of turns in primary core, and then NS is the number of turns in the secondary core. Very good, right? So this is the expression that we'll be using. So the ratio above, this ratio, okay, this ratio proves that it is possible to produce a higher voltage from a lower one, and then the vice versa, right? So from this expression, okay, you can produce a higher voltage from a lower one. You can also produce a lower voltage from a higher one, right? And that is what brings the two different kinds of transformers that we have. So if the output voltage, right, the output voltage okay, if the output voltage is greater than the input voltage, then we say the transformer is a step up transformer. This is a step up, okay? It's like you have a device, okay, you give it one apple and then it produces, let's say, 3 apples. Are you okay? It has increased the number of apples that you have. So if the output, which in this case the voltage output, is more than the input, then we say it is a step up transformer. Okay, this is one. On the other hand, if the input voltage, so if the input voltage is greater than the output voltage, then we say that this type of transformer is what we call a step down transformer. Okay, and that one again, I'll use this scenario again. If I have a device, okay, or a transformer that I give, let's say 3 apples, and it gives me, let's say, 1 apple in return, right? It means it has lost some amount of 2 apples, right? It has reduced the number of apples that I have. So that is a step down. Are you okay? Very easy. So let's now that we know these expressions, and we know the formulas that we'll be using in our calculations. So the formulas that we'll be needing is this formula 1, this formula 2, and then this expression 3. Okay, or you can just know this in your head. Okay, this is a combination of all these 3 formulas. Once you know all this, you don't have any problem, right? So now we've looked at what a transformer is. We looked at the components, okay, what makes up a transformer. We also looked at some deductions. From the deductions, we're able to establish some of these formulas that we'll be using in our calculation. We also say that if the output voltage is greater than the input voltage, that is a step up transformer. And then if the input voltage is greater than the output voltage, we call that a step down transformer. Now let me quickly draw what a step up and step down transformer looks like, and then we can continue from there. Mind you, this is the expressions that we are going to be using for our calculations. All right, so let's look at the 2 types of transformers that I said. Let's look at their drawing, right, to know what is the difference between a step up transformer and then a step down transformer. See, the only difference between a step up transformer and then a step down transformer is the number of coils, okay, the number of turns on the primary coil and then the secondary coil, right? It's just the number of turns. So for instance, for a step-up transformer, we still have our iron core like this. Okay, we have our soft iron core. Then for a step up, then it means that the number of coils on the primary side will be less. Are you okay? So because the number of coils over here is less, the input voltage will also be less, right? But then because it is a step up transformer, then the number of coils on the secondary part, okay, so the secondary coil will be more than the primary coil. Okay, now because that is more than that, the output voltage will be higher, and that is how come it is a step up transformer. Okay, it's just the number of coils, right? So everything else is still going to be the same. So we have our alternating current source, or our AC source over here. This is our AC input. Okay, and then the distance from here to here is our primary EMF. Okay, and then the distance also from here to here is our secondary EMF, and then we say this coil is our secondary coil, okay, which has the NS turns. Okay, and this part is our primary coil, okay, which has NP turns. Are you okay? And this is our AC output, okay, where our output is going to be at. So this is what we are calling a step up transformer. It's a step up because the number of turns over here is small, so the input EMF, okay, will also be smaller. But because the number of turns on the secondary coil is much higher, the output voltage will be higher. And since output voltage is more than the output in voltage, it is a step up transformer. Now on the other hand, the opposite is true. If we have our, so this is the soft iron core, right? So if we have our iron core, okay, that looks like this. Don't mind my drawing. And then on the primary core, okay, the primary core, the number of turns is plenty, right? So we have a lot of turns over here. But then on the secondary side, we have, let's say, just a few number of turns. Okay, something like this. Okay, 4 out of 1, 2, 3, 4, 5, 6. Let me even add more here. Okay, so if you look at this, obviously the number of turns on the primary side is more than on the secondary side, right? So therefore, so let me complete the drawing. So this is our AC input, okay, and then the distance from here to here is our input EMF, or our primary EMF, and then over here is our secondary EMF. Are you okay? And this is also our AC output. Okay, these are obviously our secondary core. These are obviously our primary core. Now our primary core has what? NP turns, okay, and then our secondary core has NS turns. Okay, this is our soft iron core, right? So if you look at this is what we call a step down transformer, because the input EMF is very high, but then the output EMF or on the secondary EMF will be very small. So since the input EMF is higher than the output EMF, we say this is a step down transformers. Are you okay? So these are the two types of transformers that we have. Now that we know what a transformer is, we've seen the details, we've seen the formula that we will be using. We said that the secondary EMF over the primary EMF is equal to the primary current over the secondary current, which is equal to the number of turns in the secondary coil over the number of turns in the primary coil. This expression, we can use this side as 1, this side as 1, and then just this and this also as 1, right? So we can get all our formulas from here. So now that we know this expression, let's go ahead and have some fun solving some problems on transformers. Okay, so finally we are at where we will start solving some problems on transformers. So we have this particular question, so let's give it a try and see what our results will be. So the question reads: a transformer with 5,500 turns in its primary coil is used between a 240 voltage AC supply and a 120 voltage kettle. We have to calculate the number of turns in the secondary coil. Okay, now this is fairly easy, straightforward, no much turns are on it. So let's look at our solution, right? So they say that transformer with 5,500 turns in its primary coil, so it means the number of turns NP in the primary coil is 5,500 turns. Okay, it says it's used between a 240 voltage AC supply, so the supply, which is the input voltage, right? So it means EP, okay, the primary voltage is 240 volts, and then a 120 voltage kettle, right? It means the kettle, if you plug it, is going to draw out 120 volts, so which is the secondary voltage or the secondary EMF, right? So our ES is 120 volts. So we have to calculate the number of turns in the secondary coil. That is what we do not know, right? So if you look at this is very easy, very simple. We said that the ratio of EP, okay, EP over ES, okay, is equal to, sorry, here is okay, is equal to NP over NS. Are you okay? This is the expression that we said is true. So if you look at this, no matter which one you bring first, make sure you change it proportionally. So if it is ES, we are using this and this, right? ES, NS, EP, NP, right? So over here, I interchanged it, okay? Either this, or you can bring the ES first, then the EP is equal to, make sure if it is ES at the top, it is NS at the top, and then NP at the bottom. Either way is going to give you the correct answer, right? So let's do our substitution. So let me use this one for the sake of consistency, right? So our secondary EMF is what we said, we have 120 over our primary EMF is what we have over here as 240, and this is equal to our number of turns in the secondary coil is what we do not know. Then the number of turns in the primary is 5,500, right? So from here, before I even do anything, I can cancel the 0 over here. Okay, so from here I have 12 over 24, okay, is equal to NS over 5,500. So from here I can cross multiply. Okay, I can cross multiply. This will multiply this, this will multiply this. So from here I have 24 NS is equal to here 12 multiplied by 5,500. Okay, to find NS, I divide both sides by 24 by 24. This will cancel this. So my NS is equal to 12 will go into itself 1, will go into 24 2 times. Okay, so this becomes 5,500 divided by 2, and this will give me 2,750 turns. Okay, so this is the number of turns on the secondary transformer. So we have 2750 turns. Okay, now if you look at it, the number of turns in the primary transformer is 5500, and half of it is what we have on the secondary transformer. So it means if this is the my transformer, okay, it means let me use, this is 5, so let me use the primary, let me use 5, 1 2 3 4 5, right? It's more than that, but I'll just use the first digit. So this is like, let me say 2.5, right? So this is 1 2 something like this, right? 3, let me make it like that, right? So if you look at this, this is obviously a step down transformer, okay, because the input voltage, even if you are not using the number of turns, the input voltage is 240 over here, and then it is giving you a 120 voltage for your electric kettle to be able to use, right? It doesn't blow, right? So it is stepping down the EMF for you. So this is obviously a step down transformer. Are you okay? All right, let's look at the next question. We have a transformer which has a 300 turns of wire in the primary coil and 30 turns in the secondary coil. If the input voltage is 100 volts, we have to find the output voltage, right? Now, already from reading the question is saying a transformer has 300 turns of wire in the primary coil. So the primary coil has 300 turns, and the secondary coil has 30 turns. This is also a step down transformer, right? Because of the number of coils that we have in both primary and secondary sources. So if the input voltage is 100, find the output voltage. So from here, we know that since it is a step down transformer, the output voltage should be smaller than the input voltage. So if I get an answer which is more than 100, I should automatically know that my answer is wrong, because it is a step down transformer, and so therefore my secondary voltage or my output voltage should be less than the input voltage. All right, so let's write down our solution. Okay, so they say the number of turns in the primary coil is 300, and then it has 30 turns in the secondary, so NS is 30. The input voltage E primary is 100 volts, and then we have to find the output or the secondary voltage. That is what we do not know. Okay, so just like we did before, we have our secondary EMF over primary EMF is equal to the number of turns in the secondary over the number of turns in the primary over here, right? So from here, let me make ES the subject. So I'll first of all cross multiply. So ES multiplied by NP is equal to EP multiplied by NS. So I have EP here multiplied by NS, right? So we want to find ES, so I divide both sides by NP. So this will cancel this. So my ES is equal to my EP is 100, which is my primary voltage, multiplied by my secondary turns, which is 30, divided by primary 10 NP, which is 300, right? So from here we can compute to find our output voltage. So the 0 here will cancel the 0 here, the second one will cancel this over here. So I have 10 multiplied by 3 at the top, that will give me 30. Then I have 3 at the bottom here, so this is equal to what? 10. 30 divided by 3 is 10. So 10 volts is my answer. And like I said, obviously the output voltage is smaller than the input voltage, so it's 10 to 100. So it is a step down transformer, like I said, and this proves that my answer is indeed correct. All right, let's have a look at one final example. So they are saying if the efficiency of a transformer is 80% and the current in the secondary coil is 10 amperes, we are to calculate the current in the 240 voltage supply provided the output voltage is 24 volts. Are you okay? So this is also a very simple problem. So let's write down our solution and look at it. They said that the efficiency of the transformer, the efficiency, okay, the efficiency is 80%. Okay, and then the current in the secondary core, so IS, is 10 amperes. We have to calculate the current in the, okay, so in the, so we have to calculate the primary current, which we don't know, in the 240 voltage supply. So supply means what? EP is a 240 volts. If the output, which is ES, is what? 24 volts. Are we okay? All right. So if you look at this, we are looking at a supply voltage, a primary voltage of 240, supply voltage of 24. So obviously this is a step down transformer. All right. So when we talk about the efficiency of a machine, okay, is equal to power input. Okay. So power output over power input multiplied by 100, right? That is what is going to give you the efficiency, right, in percentage. Okay, so we can divide this, since this is multiplying this, so to get rid of the 100 over here, so we can leave that like that. So let's leave it like this for now. So the efficiency, when you have this in percentage like we have over here, then you take off the 100 over here. So if you have the efficiency already given to you in percentage, it's just equal to what? Power output over power input, right? Because the percentage has already been brought over to this side. Okay, so which is what we are going to do now. What is power output? Power output is voltage times current. So obviously it's equal to ESIS. This is the power output. Okay, then the power input is EPIP. That is the power input. So the efficiency, we are going to use this version of the formula. The efficiency given to us is 80%. So it's 80 over 100, which is equal to our power output is ES multiplied by IS over EP multiplied by IP. So I have my 80 over 100, which is the 80%, is equal to my ES is 24 multiplied by my IS, which is 10, all over my EP, which is 240 multiplied by IP, which I do not know. So from here we can go on and do some few cancellations and then get our answer. Obviously this will cancel this, so we are done with this side. The top over here, if you multiply 24 by this, so let me make it like this, this is 8 over 10 is equal to this multiplied by this is 240 over 240 multiplied by IP. So this will go into itself 1, go here 1, right? So we have this is equal to 8 over 10 is equal to 1 over what? IP, because this has cancelled each other out. So 8 will cross multiply over here. Okay, so it becomes 8 IP is equal to 10. Okay, 10 multiplied by the 1 at the top. So we divide both sides by 8 by 8. So therefore our IP will be equal to 10 divided by 8 will give us 1.25 amperes as my answer, right? So this is my answer for this particular problem. And now if you look at it, because we are saying that the primary voltage is more than the secondary voltage, we are saying this is a step down transformer. Now because it's the step down transformer, and then the relationship between the current and then the EMF is inversely proportional, you can see that even though the primary voltage is more, the current in the primary core is also lower than the secondary one. Are you okay? So which makes sense, but the number of turns will be more. The number of turns is directly proportional to the EMF, but inversely proportional to the current. So that makes sense. So thank you so much for watching. This is just some few questions on transformers. We'll be looking at more questions, and then we'll move on to the past questions related to transformers. Okay, so thank you once again, and I will see you in the next video. Bye bye.